In the year 1820, a scientist named Hans Christian Ørsted is performing experiments with current carrying wires. Then he observed some deflection in the compass which is kept near to the wire. This led to the great discovery of electromagnetism, and he performed a simple experiment and he observed many things with that experiment. This is the experimental setup he has. This is copper wire which is connected to a battery, and here one compass is kept. When the connections are not made, means the battery is not included in the circuit, he kept a magnet near to the compass. Then the needle of the compass deflected and he took out the magnet and he included the battery in the circuit by connecting the positive and negative terminals. Then also he observed the same thing, that the compass needle deflected, and we know the compass needle deflects only in magnetic fields, but here is no magnet. Even though there is no magnet, the compass needle is deflecting. This means this current carrying wire itself producing magnetic field. With this experiment, he found many new things. First one is, current not only gives heat and light but also make things to turn. Here this current carrying wire make this compass to deflect. So current also makes the things to turn. This is used in making ammeter, voltmeter, and many household appliances like mixer, I mean to say grinder, fans, washing machines, whatnot. So in all the things this effect is used. And second one is, till 1820, electricity and magnetism are considered to be different subjects or different phenomena. But after conducting this experiment, there is some connection between electricity and magnetism. And if the current is increased, here one battery is there, if you add one more, then the needle deflects more. Means if the current is increased, the deflection increased means the magnetic field also gets stronger here. I mean to say, by the increase of current, the field around this current carrying wire is also increased and the field gets stronger. Near the wire, the field is stronger, means the deflection is more. If you move this compass away from the wire, away from this wire, then the deflection becomes less and less, means that the magnetic field is becomes weaker and weaker as we move away from the wire. If you keep the compass below the wire, the deflection will be in one direction. Keep the compass above the wire, then the direction of deflection is reversed. If the current is in one direction, then the deflection will be in one direction. If you change the direction of current, the deflection is reversed. This is a current carrying conductor and this is cardboard. The current carrying conductor inserted into the cardboard, and you have to keep the magnetic compass around this current carrying conductor at different positions, and you have to point the north pole, and we can draw a circle connecting all the points. This is magnetic field line, and the direction of field line will be tangent at any point. If you want direction of field line at this point, and you have to draw a tangent so that it will give the direction of field line. And if you keep the magnetic compass a little far than the first magnetic line, then it will be another circle, and we can draw many more like this. The magnetic lines will be like this, and if you observe carefully, the circles are closer, and if we move far, the circles are farther. Means the strong magnetic field is near the wire, and the magnetic field becomes weaker as we move away from the wire. And the magnetic field lines are concentric circles which have center on the wire. If the direction of current is reversed, the direction of field is also reversed. Magnetic field lines due to a current carrying straight wire. This can be explained with the right hand thumb rule, according to which if you keep the current carrying straight wire in your right hand, and if the direction of thumb gives direction of current, then the direction of wrapped fingers or the curling of fingers gives the direction of field lines. So this is the current carrying conductor, and the current is in this direction because the thumb is shown in this direction, so the current is in this direction. Then the curl of the fingers. So fingers are curled like this. If you hold the current carrying conductor, current carrying wire with your right hand, then the fingers will be curled in this direction. So this direction gives the direction of field lines. And one more thing is, if the current is in upward direction like this, then the field lines are anti-clockwise. If the current is downward direction, then the direction of field lines will be changed, and then it will be clockwise direction. Magnetic field lines due to circular coil. This is the circular coil which is shown in the red color, and to find the magnetic field lines you have to use the right hand thumb rule at each and every point of the circular coil. For example, if you consider this point, then you have to keep your thumb in the direction of current, and the curling of fingers will give you the direction of field. In similar way, if you want here, then here you have to keep your thumb in direction of current, then the curling of fingers will give you the direction of field. If you observe the field lines produced by the circular coil with the field lines of a bar magnet, those are almost equal. Here the field lines are somewhat elliptical, and here these are circular. If you make this bar magnet of little size, means a tiny bar magnet, then the magnetic lines of tiny bar magnet resembles with the magnetic field lines of circular coil. And if you observe inside the coil, magnetic lines direction is upwards like this, and outside the coil this is downwards like this. Magnetic field due to a solenoid. A solenoid is a type of electromagnetic formed by a helical coil of wire whose length is greater than its diameter. Here this one is solenoid, and his length is more than its diameter. The current is passed in this direction, and current is leaving the solenoid from here. Here also the right hand thumb rule is used to find out the direction of magnetic field lines. If you observe, the magnetic field lines of solenoid and the magnetic field lines of bar magnet resembles same. Inside the solenoid, the field lines are from south to north, and outside the solenoid, the field lines are from north to south, same as the field lines in bar magnet.
Electromagnets have more advantages than permanent magnets because if current is increased, then the magnetic field is also increased and vice versa. If we switch off the current, then there is no field. If we change the direction of current, then the direction of magnetic field is also changed. In MRI like machines, always there should be the change in magnetic field. So electromagnets are used in MRI like machines, but the permanent magnets are not used there. Soft iron can be made magnetized and demagnetized easily. So the temporary magnets can be manufactured with soft iron, and with hard iron, it is hard to demagnetize and magnetize. So permanent magnets are made with hard iron. Magnetic flux. Magnetic flux is the number of magnetic lines passing through the plane of area A. This is plane of area A, and these are the magnetic lines and the number of lines passing through this area. If you consider here, number of lines passing here is 1, 2, 3. So the flux here is, the magnetic flux here is 3, and the SI unit of this is Weber. If you consider a unit area in this, then the magnetic flux passing through unit area perpendicular to the field. This is the direction of field, this is area, and if you consider a unit area here, then the magnetic flux density or magnetic field induction, which is given by B is equals to phi by A. Its unit are Weber per meter square, or you can write as Tesla. Take these two figures. Here the area, the plane of the area, and the lines are perpendicular to each other. So the maximum number of lines are flowing through the area. So here maximum flux is present. This is the area where these two are parallel, the plane of area and magnetic lines. Then the flux here is minimum. Consider theta is the angle between the magnetic lines and the normal drawn to plane of rotation. This is theta. Then the magnetic flux density given by pi by a cos theta. So pi is equals b a cos theta or b dot a. Consider this case in which the normal drawn to plane of area, this is area, and this is the normal drawn. So the angle between these two is 0 degrees. So from this, pi is equals to b a cos 0, which is equals to 1. So just this is b a. So flux is maximum in this case. If you consider this case, the normal drawn to this plane will be in this direction, and the magnetic lines are in this direction. So the angle between them is 90 degrees. Here in this case, the magnetic flux is equals to B A cos 90. The value of cos 90 is 0. The flux is equals to 0. So this is the case of maximum flux, and this is the case of minimum flux. Now the magnetic force on moving charge. This is moving charge Q. It is moving with velocity v, and this moving charge is moving perpendicular to the magnetic field. These are magnetic lines. We can get the direction of force from this right hand rule, which states that if the index finger, middle finger, and thumb are stretched in perpendicular directions to each other, and if your index finger shows the direction of velocity of charge or current, and your middle finger or the center finger shows the direction of magnetic field, then your thumb gives the direction of force. Here the force is given by F is equals to QV B when these are mutually perpendicular. There is an angle between B and V, means they are not perpendicular and the angle between them is theta. Then F is given by QVB sin theta. Due to this force, this electron moves in circular path due to the centripetal force.
Magnetic force on current carrying wire. Consider this is north pole and south pole of magnet, and there will be magnetic field or the lines of force from north to south. Consider a current carrying wire, a straight wire, in which the current is in this direction. We observe there will be some movement in this wire because the current carrying conductor acts as a magnet, and here we have another magnet. Due to these two, there will be moment in this current carrying conductor, means there will be a resultant force, and we are going to find out the direction of that force. This will be done with Fleming's left hand rule. This is Fleming's left hand rule. When you keep your thumb, middle finger, and index finger in mutually perpendicular directions, and if the middle finger shows the current, direction of current, instead of middle, let us consider it as center finger. So center finger shows the direction of current, and the index finger, instead of index finger, let it be forefinger. Forefinger shows the direction of field, magnetic field. Then the thumb gives the direction of force or direction of motion. This is the Fleming's left hand rule. Let it is the direction of field, and this is the direction of current, and this will be the direction of force. The direction of current is reversed, means if the current is moving upwards, then if you stretch the fingers applying this rule, here the force is outwards, means in the previous case when the current is in downward direction, when the current direction is upwards and field is in this way, then there will be, this is current direction and this is field direction, then the thumb will give you the direction of force. This is inwards. When the current is upwards, then the force will be inward. When the current is downwards, then the force will be outwards. When a current carrying conductor is placed in magnetic field, then it experiences some moment, and in our previous topic we found that the force is equals to BIL sin theta, where theta is the angle between the current and the field, and L is the length of the conductor. So what will happen if we keep a coil instead of a wire. This is a coil. The conventional current is supplied in this way. So current moves here and it will be like this. Now the field from north to south. So what will happen? Here the direction of force is given by Fleming's left hand rule. The same thing should be applied here. This is Fleming's left hand rule, in which the three fingers, middle finger, index finger, and thumb, are stretched in mutually perpendicular directions to each other. Then, if the middle finger or the center finger shows the current and the forefinger shows the field, then the force or the motion is given by thumb. Apply the same rule here, here, and here. If you see here, the current is in this direction, which is perpendicular to the field. If current is perpendicular to the field, then there will be force. And for our convenience, let us consider this as A, B, C, and D. So in the side AB, you have the force is maximum, and there will be rotation. If you stretch your three fingers, showing the current, field in this side of coil, then the force will be upwards, means it rotates upwards, means the force is outside. At the same time, the current flows from here to here. So this is parallel to the field. So it is equals to 0 here. And here the current is, the conventional current is downwards. If you apply the same, then the force will be downwards. Force will be downwards. And if you consider this case, here the force will be downwards. So in this part of the coil, there will be maximum force, which is equals to BIL, and this is again parallel to the field. So there will be zero force, and these two are equal in magnitude. When the two forces are equal in magnitude and applied in opposite directions, then there will be a turning effect, so which is the concept of couple. But what will happen if this side moves up and this side moves down? There is no further movement. So some attachments should be made to make an electric motor. This is electric motor. This is south pole of magnet, this is north pole, and this is the battery to supply the current. And you have, this side is attached to a slip ring, and this side is also attached to this slip ring. And these two, this one and this one, these are called brushes. This coil is called armature. If you supply the current by closing the key, then there will be current flow. Just now I explained what will happen if you supply current. After half rotation, this slip ring will be attached to this brush, and this slip ring will be attached to this brush. So there will be continuous rotation. So this arrangement works as an electric motor. This is a simple experiment to explain electromagnetic induction. The materials needed for doing this experiment is a wooden base, copper wire. This copper wire is winded on soft iron cylinder, and we need a metal ring. When this metal ring is placed here, and if you connect this copper wire to AC source, then it will jump into air. If you keep the metal ring slowly from the top, and if you switch on AC, then the metal ring deviates like this, because the AC current is alternating current in certain time intervals. The magnitude and direction of the current is changes. So due to the current supply, this copper wire, the winded copper wire, behaves as solenoid, and you know well about solenoid. What will happen if current is passed through the solenoid? Because it was explained in this chapter, and the magnetic field will be produced, and due to the magnetic field, this metal ring also have magnetic field, which is called induced magnetic field. This is because of the magnetic field produced here. So this is called induced magnetic field, and it is opposite to the magnetic field produced in the solenoid. Due to the magnetic field, there will be current which is called induced current. This is in opposite direction to the current in the solenoid. Why it is leviating means the net force is 0 here. If we replace this with this metal ring with other metal ring which is having more cross sectional area, then also the leviation is same. Why? Because when the area of cross section is increased, the resistance decreases. Resistance decreases means the current flows more. So the same leviation takes place here and here. If this ring is splitted, means there is a gap at the ends, then there is no leviation, because the current will not flow through the ring. Very small experiments made Fleming and Lenge has to give their laws on magnetic induction. A simple experiment is here. A solenoid is created like this, and it is connected to galvanometer. This is a bar magnet with north and south poles. When there is no motion of magnet, means the magnet is stationary, then the deflection in galvanometer is like this, means there is no deflection in the galvanometer. When the north pole of the magnet is moved towards the coil or solenoid, then the deflection will be right and the current direction is like this. When the magnet stops moving, then there is no deflection again in galvanometer. When the magnet made to move back, means the magnet is taken out like this, and in this case magnet is in forward and it is in backward, then the current direction is changes, and in previous case current direction is like this and galvanometer in this direction. In this case current direction is reversed and the galvanometer deflection in is in opposite direction like this. The deflection increases if the magnet moves with great speed. If you the speed of the magnet is increased, means if it is slow, then the deflection will be slow. If the magnet is rapidly moved towards the solenoid, then the deflection will be more. If the polarity reverses, means if the magnet is reversed, here north is moving towards solenoid, if south is moving towards solenoid, then the deflection of galvanometer. The deflection of galvanometer gives the direction of current. That's why the direction of current is also reversed. By this Faraday observed, current flows in the coil only when there is a relative motion between coil and magnet.
If the direction of motion is reversed, current direction is also reversed. Current in the coil can be increased by increasing turns, means the number of turns of the solenoid coil can be increased, or we can use a strong magnet so that the current can be increased. This current is called induced current, and speed up the magnet. How rapid the magnet moves, the deflection is that much more, and the induced current will be more. When there is relative motion, flux changes, EMF is induced, causes current to flow through it. The direction of induced EMF depends on increase or decrease in the flux. With these simple experiment observations, Faraday and Lynch has given their laws. Faraday's law is when uh, there is a continuous change in magnetic flux linked with the coil, a current is generated and is called induced current, and the generated EMF is induced EMF and is equals to the rate of change of flux, that is d phi by dt. In similar way, Lenz's law is the induced current will appear in such a direction that it opposes the changes in the flux in the coil. This is AC generator. The simple diagram of AC generator will be like this, and it works on the principle of Fleming's right hand generator rule. This right hand generator rule gives the direction of induced current in the generator. If you stretch your thumb and index finger or forefinger and the middle finger or center finger in perpendicular directions to each other, and if your thumb gives the direction of force or motion of the conductor, and if your forefinger gives the direction of magnetic field, then the center finger gives the direction of current. This is applied to find out the direction of current in AC generator. This AC generator contains an armature. Armature means a coil, and this coil is placed in between north and south pole of a strong magnet, and the ends of the armature is connected to slip rings. This is one slip ring and this is other. One end is connected to this one and other is connected to this one. If the slip rings are not there, then there will be twisting in the wires and generator will not work. If you give slip rings, then the ends will rotate inside the slip rings and there is no twisting. And these slip rings are attached to carbon brushes, and the carbon brushes are attached to the load. Now consider the armature is like this. This is side B and this is side A. Let us consider our we are made to rotate this armature in clockwise direction, and B is at the top and A is at the bottom. The field is always from north to south poles. In this position, this armature is not affected by any field. So the induced current will be 0 here, and we can find out the current direction using this, and it will be like this. The current is in this direction. When this is gradually rotating, the induced current is gradually increases because this armature is affected by the field lines. So current will be induced and it is gradually increase and becomes maximum at this position. In this position, B will be here and A will be here. Imagine it is here, and at this position, this armature affected by maximum field. So there is maximum current at this position, and again the rotation continues, and the current gradually decreases because the effect of field is decreases and the induced current will be decreased, and it will be gradually decreases to 0 when B comes here and A moves to top, and the rotation continue, but the direction of current changes, and here this is B moves like this and A moves in this direction, and this is the current gradually increases but in opposite direction and becomes maximum at this position. This is B and this is A. Again the rotation continues and B moves up and the current induced current gradually decreases and becomes 0 here. This is for one cycle. AC generator works like this. This is DC generator which contains an armature which is placed in between north and south poles of strong magnet, and this is made to rotate to generate current, and these the two ends of this armature are connected to split rings. In AC generator we connected the two ends to slip rings so that the current is in both the directions, but here in DC generator we are getting unidirectional current. That's why these slip rings are replaced with split rings. Here also we use Fleming's right hand generator rule to find out the direction of current. If the force is upward, I mean if we made the rotation in clockwise direction, this will move up and this will move down. In that case, if the force is up and field is always from north to south, magnetic field in this direction, then the current will move like this in this direction. If the force is in downward direction, when this is moving in this direction, then the force is in downward, field is in this direction, then the current will be downward direction. When the rotation is made in clockwise direction, let us consider B is here, means the direction of B is up and the direction of A is down. Then the magnetic field will not affect armature, means there is no induced EMF, so the current generated is 0. When this B rotates like this and A will move upwards, the armature affected by the field, so the induced current gradually increases and becomes maximum when it B comes here and A here, because there is maximum effect of field here, so the current is maximum. After that B comes downwards and A moves here, and at a stage where it is like this is A and this is B. In this case, from this to this, again the effect of field reduced and comes to 0 at this position. In AC generator, due to the slip rings, direction of induced current is reversed. But here, due to having the split rings, this split ring is attached to this one and this split ring to this. So the direction of current will not change, but again this B moves up and the current gradually increases and becomes maximum when this B comes to here. I mean when it makes like this, when it is like this, the total field is affected here and this is BA, and finally after this B moves up and A comes down, so that the current again gradually decreases and becomes 0. This is for one cycle. In this way, DC generator works. It gives unidirectional current.